Okay, this is a follow-up to two earlier video segments where I actually showed you how to solve a single degree of freedom system using the Catia program, but I labeled these videos as killing a fly with a cannon series because the problem is simple enough that can be done in with hand calculation, and in fact, you can find in any elementary vibrations book. However, uh, one really should be able to know at least how these are done in the Catia program, which is a lot more sophisticated when it comes to doing FEA on it than this particular problem. The situation is as follows. The difference between this current video and the earlier two is that the very first one that I did was where I had an initial displacement specified. It was a free vibration problem. So basically, it's this mass displaced to the right and released. So that was the earlier video. And then in the next video, I showed you how to force or trick Catia to do a initial velocity uh, uh, condition. Okay. That was using the impulse function. The thing is that in Catia, you don't have free vibration. You have to do everything as a forced vibration, and there's no provision for specifying initial conditions in it either. So we basically have to trick it to do the thing that we want. This particular video is when you have both initial displacement and initial velocity specified, and it's an undamped free vibration. So the detailed information is given here, and the natural frequency is 2 rad per second, which translates into this in hertz, and the period, which is 1 over that hertz, is going to be roughly 3.14 seconds. Now, the thing is that we have both initial displacement of 0.5 meter and initial velocity of 2 root 2, which is about almost 2.3 meters per second. Now, the analytical solution for this is given right here. And notice that the amplitude of the vibration is 1.5 meters, and there is a phase difference, phase angle here too. So whatever we do, we really have to compare it with this, okay? And specifically, I'm going to compare my displacement amplitude for this comparison purpose. In Catia, there's no provision for initial values being specified, and also it's based on linear dynamics. Now, what that means is that the natural frequencies have to be extracted. In this case, there's only one of them, of course, and then using the forcing function and the Duhamel integral, one can find the response of the function as a function of time. Now, this is, of course, the steady state response of the function as a function of time, or well, assume that the initial conditions are 0, okay? So the way I did my second video where I actually modeled initial velocity, I used the concept of impulse. So the force modulation that will be defined in Catia is a curve like this. So initially everything is 0, and over one period, which is very slowly, the mass is pulled to the right, for example, so that it reaches that position of 0.5 meters. Now, 0.5 meter, if you multiply it by the stiffness of the spring, you get 2 newtons. So this is why after one period, the force is applied and it moves that thing to the point, to the location 0.5 meter, which means at the end of this linear time variation, you're going to have 2 newtons applied to the mass. Now, at that instant, we give it an impulse, so that over a very short period of time. So, if you go back to your vibrations book, you see that the area under this curve is actually called impulse, and it's mv naught. So, if m is 1 and this impulse has the correct area, then you're going to get the initial velocity out of that. okay? And then we drop the force. During that short period of time, the impulse is applied, a very large load is applied, and then drop down to zero, and of course becomes a free vibration problem. So this is how we trick Catia to do a free vibration problem with initial conditions specified. Now, there are different ways of modeling the spring. The one that I used in the earlier videos was the concept of a spring rigid type of connection. So just remember, we're going to be using this. And also, when you do transient dynamics to find this response as a function of time, the number of steps plays a critical role in the accuracy of the results. So excuse me, I'm going to run this thing for two different number of steps. One is 200 and show you that you're not going to get the 1.5 amplitude as you're supposed to. And then I'm going to make the number of steps is 2000. And you see that we get right on the dot the value of 1.5 that we want for the amplitude of the oscillation. Okay, so let's go ahead and do this. We go to Catia and let me close this thing. All right, and we start with the parts file. So let's start with the part file. And I create my spring by first creating 2 points, a line in between them. And then, of course, I have to mesh that line with beam element, but I'm not going to be using it. Okay, you have to do it, but you're not going to be using it. And then you create the spring through a user-defined connection. So let's create our points here. This is the first point at the origin right now. The second one, I'm going to make it 1 meter away in the y direction. So my spring is going to be, my spring is going to be aligned in the y direction. Okay, right there. And then I create a line from here to here. All right, let's apply material properties to this. So apply material properties. I'm going to use the dummy aluminum applied to that. The actual material is irrelevant as long as you make it a very small stiffness and mass, a very small density. So the Young's modulus for aluminum is 70 GPa. I'm going to make it 0.1, which is pretty much nothing. And the density of the aluminum is 2,700 kilogram per meter cube. So I'm going to make it 0.1 so that these will not affect my spring properties. Now we're going to switch to generative structure analysis. This line, we're going to mesh it. This element is not going to be used, but you do have to mesh it. So here's the beam element. We can see that right there, beam element. Let me move this thing out of the way so that you can see what's going on here. Yeah, it's called Model Manager. And here's the beam element. You click on it. And notice that this length was 1, and here I'm going to say element size equal to 0.1. So in principle, there should be 10 elements along that line. But if I say minimal mesh and select that, it just put one element from left end to the right end. That's all I want. Okay, by the way, I could have made the element size to be 1 and select this. There will be 1 element from this end to the other. Now we need the dummy cross section here, so we're going to apply the 1D properties, select that, and this is a dummy radius of 0.05 meters. That'll do nothing, it's just that we have to do it, otherwise you can't do the rest of the problem. Now I'm going to hide these points because I don't want inadvertently put restraints and loads on it, because Catia will not recognize it. The Catia FEA will not recognize it. Now we have to create a connection, analysis connection. Let me move these things out of the way. Analysis connection, general analysis connection between this point and for the second component, that point. We close it. Notice that analysis connection has been created here, and we're going to make that thing a user-defined connection right there. User-defined distant connection property. Click on it. The only thing that you can pick from the tree is this connection. And because it's going from point to point, the only thing that you can take are just the middle section. So in the previous videos, I used the spring rigid, so I'm going to stick to that. And I click on this wrench here. It says that the stiffness along the y direction is 4 Newton per meter. Okay, very good. Let me close that. Now, let's apply some restraints here. So this end point, I'm going to clamp it. We're doing a static analysis first, okay? Although that's not the thing that we want, and then user defined at this end. The only thing that's allowed to move is along the y direction. And then I apply a force of 1 Newton at this end. Where is that? This is the force under load. Let me bring it here so that you can see it better. Load, distributed force at that point in the direction y, 1 Newton. So obviously, if the stiffness is 4 and you pull this thing by 1 Newton, this is going to deflect by 0.25 inches. And it not inches, meters. Okay, so let's go ahead and run it. Nothing exotic is going to happen. Good, and if you look at the displacement, all you see is 0.25 meter. That's good. Now, when we are done here, we're going to say insert frequency case with the restraints being the reference element from the one that we just did, the static one that we just did, which I believe is here. We're going to use the same restraints. And if you double click on this, you see that it says that we're trying to extract 10 frequencies, but this is a single degree of freedom system now, so we better put it this thing 1. Otherwise, it comes back with an error message saying that you're asking for 10, you have only 1. So you have to go back and change that thing to 1. So I did it right now. That's pretty much it. So if you run, oh, I forgot to put the mass here. There's a mass of 1 kilogram there. So look at the inertia or mass here. Here's the toolbar for it, right there, masses. Click on it. You select this point, and you put a value of 1 kilogram. So it's going to be a mass at that time. You can actually see that. See this? See the mass? Okay, it's just the icon for the mass. Good. So we're going to run it. And there's really not much here. There's going to be one frequency that's going to get extracted, and it should be 0.317 hertz. So there we are. It's done. Under the frequency on the list, nothing unusual, 0.318 hertz, and that's exactly what we had here as 0.318 hertz. Okay. Now we want to do this transient dynamic problem. So we're going to do an insert transient dynamics. Okay, so the frequency case, you have to do a frequency case, and we already did it. So we're going to select it from the tree right there. See that? It puts it in here. And it's a load excitation, so that's when everything else is the same. You say, okay. Now, first of all, if you go here, we have done several videos using these tools. So if you go to damping, double click on it. You click on the wrench, it automatically puts 1% damping on all the modes. There's only one mode here, so we make that thing 0 because our problem is undamped, right? Okay, good. That takes care of this. Now, if you double click on Transient Dynamics here, okay, let me make the steps 200, okay? And we go from 0 to 10 seconds. So let me make this thing 0 to 5 seconds. How about that? And the reason is that the time that I'm going to put is going to be from 0 to 5. So that's okay. So it's going to be basically calculating from 0 second to 5 seconds. And the number of steps is 200. This is going to give you something that is not the 1.5 that you're targeting at. That amplitude, if you go back here, you see the amplitude is supposed to be 1.5. You're not going to get 1.5 anyways here with this number of steps. Now, okay, so if you double click on the load excitation, you're going to see that it's asking for the load. The load is that one one Newton dummy load that we put in the static case, which is further up here, there. But it's also asking for modulation. Now, what that means is that because we're doing a dynamic problem, you have to give you the force as a function of time. And I had to create an Excel spreadsheet, which is right there. So I have to import this as my modulation. Notice that from here to here is 1 Tn, 1 natural period, and from here to here is 1/100th of a Tn. Okay? And those are reflected in this figure. That's the same thing. Okay, good. All right, so let's remove this thing. I haven't imported my modulation, so I'm going to cancel that. And notice that here there is a modulation toolbar right there. And the one that you want is a time modulation right here. This is white noise, this is frequency modulation, this is time modulation. And that's only a fancy way of saying what is force versus time. You click on it, it says, okay, go get it. So I have to create that Excel spreadsheet, and I have done it already. So I go to Browse, and it's right here. Initial displacement, initial velocity, and the impulse is during 0.01 Tn. Okay, that's the one that I want. So you select this, say okay. All right, and we close it. Notice that here a modulation has been created in the tree right there. And then I'm going to do again that load excitation. For the load, I'm going to select that static load, which was right here. And for modulation from the tree, I'm going to select that thingy. By the way, you can plot this thing if you put the cursor on the modulation that you imported, right click, 2D plot, and you're going to get that same plot that I showed you. Okay, so linearly varying the displacement, the mass, and then suddenly a big force, which means you're importing an impulse over a short period of time, and then drops to zero. So that's the same thing. Okay, good. Now, that's pretty much it. There's nothing else to do. So what you do is everything that needs to be done is already accomplished. The frequencies have been extracted, damping has been set, modulation has been set, and now you're going to say right-click, generate to. I have to solve it. So yeah, I have to solve. Actually, let's try to solve it. I can't remember whether we have to solve it or not, but maybe I do. Maybe I do. So let's go ahead and do that. Now it looks, maybe not. Right click, yeah, because these things were not there. If you want to get these things there, then you probably have to solve it. So generate 2D plot. You click on it next. Only one graph. We just want displacement. We don't want velocity, etc. Actually, let me do two graphs, both displacement and velocity. We'll see that. Finish. Okay. It says, all right, where is that thing? This top one is the one of them is the, can't remember. One of them is velocity. The other one is displacement. But that's okay. It says, where is your node that you want to actually pick? And this is the node that I want to pick. But notice that it's blocking my view. I cannot block my selection. So if you can hide these things, right click hide. Still can't block it. Right, you can pick it, hide, and now you can go and select this node 1. Okay, and say no. Notice it was selected here. You say add. Okay, and notice that the layout is displacement and velocity. So the top one is probably displacement, the bottom one is layout. You say okay. That's pretty much it. So if you put the cursor there, right? If you double click on this, you will get your displacement and velocity curves right there. Now let's close some of the stuff that we don't want. I'm going to close this and I'm going to close that. And these things are blocking my view. So I'm going to say, I'm going to put all of these on the sides. Tools, customize. The usual thing that you do to clean your screen. Customize under toolbars, restore positions. Okay, so it's going to push everything to the side. Okay, so that's good. The only thing that I don't need is this guy. I'm going to delete it. Now, this one is one of them is this one. One of them is, this one is velocity, I'm sure, because look at the unit meter per second, and this is the displacement, but it's the amplitude. So I want to change this thing to real instead of amplitude. Notice that this goes to 5 seconds, and this one again, right click, format, we go to real, and this also goes to 5 seconds. So a couple of things that I'm going to show you. First of all, uh, uh, look at the magnitude of the oscillation. Now I didn't go to 10, so maybe I should go and repeat this thing for 10 seconds. So I'm going to close this. Let's go back to our transient dynamics, and we're going to go to 10 seconds so that we can see everything. My Excel spreadsheet went all the way to 5, so let's hope that this will not cause a problem. Otherwise, I'll have to go and fix that thing. And double click on this. Yeah, it goes all the way to 10. It didn't bother. Now, but the amplitude is not what I'm supposed to getting. This is the amplitude of the displacement, which is supposed to be what is that? 1.5. Okay, and the velocity, there should be a sudden jump, and it is. The sudden jump is there. This is one period. You can see that one period, slowly changing it, reaching to that 0.5 meter displacement, and then give it an impulse. The only thing is that these values do not match what I'm supposed to get. Like this one should be, this amplitude should be 1.5. It is not. So the key is that number of steps. So you go back here. Let me close this. The number of steps here, instead of doing 200, I'm going to go, for example, 2,000 or 1,000. Let me try 1,000. I'm pretty sure 1,000 is going to work fine. So now let's go ahead and plot it. We close this. There we are, 1.5. You see that? This is the amplitude of the displacement, 1.5, and this is the jump, which is roughly 2.28. Remember 2.28, the impulse? Where is that thing? Right here. If you saw, it said m equal to 1 solve for v naught, 2.8, not 2.28. Yeah. So let's see. Yep, jumps to 2.8. So I showed you how to take the Catia program and apply, take a case, for example, of mass spring system, no damper here. In other words, we're going to assume that damping is 0. And in fact, all the videos that I've done so far, damping have been taken to be 0. But anyway, it shows you how to trick it so that it handles the initial displacement and initial velocity through that impulse. And that takes care of this video. Remember, you better be careful about this. The way people usually handle this, they start with a number of steps, and then they try maybe double the number of steps 10 times, and then again double, or again 10 times. Once things don't change that much, it means that that number of steps is the appropriate one to use. All right, folks, good luck.